Energy fluctuations of systems in thermal contact. Consider two macroscopic systems A and A prime in thermal equilibrium at the absolute temperature T. Let C and C prime denote their respective heat capacities when their external parameters are kept constant. Use the results that were derived earlier to show that the standard deviation of the energy of the system A is given by this expression. Okay, so first of all, I would like to remember um, when we encountered these results A32 and A37. So this was derived in the video on magnitude of energy fluctuations, where we had two macroscopic systems A and A prime in thermal contact, and we were looking for the most probable energy value, and we have the probability distribution that is expanded into a Taylor series around this value, where we have defined from the Taylor series expansion, we have used gamma as minus del beta del E at the most probable energy, and gamma prime is basically minus del beta prime del E prime at the most probable energy. Gamma 0 was the addition of these two, and we found that the probability was decaying exponentially with e to the minus 1/2 gamma 0 epsilon square in the vicinity of the most probable energy, and the magnitude of the energy fluctuations was gamma 0 to the power minus 1/2. So that's basically what we found, and eventually that led to the conclusion that the relative magnitude of fluctuations goes as 1/√f. So I'm importing all of this into this problem. So I have gamma definition, gamma prime definition, and gamma 0, and the magnitude of energy fluctuations given by gamma 0 to the power minus 1/2. Okay, so let me start with the heat capacity. On the other hand, heat capacity is defined as del E bar del T for system A, and when the external parameters of A is kept constant, and the heat capacity of system A prime is del E prime bar del T, where the external parameters of the A prime system are kept constant. So let me look at the gamma value. So this gamma value was basically minus del beta del E. So I can write this as minus del beta del T del E. Okay, so if you do this in the most probable energy, this would be del T del E bar at that point. So because del E del T is C, this would be minus 1/c, and on the other hand, beta is defined as 1/kt. So this would be equal to minus, the derivative is minus 1/kt square, and then del T del E is 1/c. So this minus sign would disappear, and I would find that what I'm calling gamma is 1/capital C kt squared. And similarly, gamma prime would be 1/c prime kt squared. They have the same temperature because they're at thermal equilibrium. So what I call gamma 0 would be gamma plus gamma prime. This is in 1/kt square parentheses 1/c plus 1/c prime. So let's do this calculation. So gamma 0 would be equal to 1/kt square. So it would be c prime plus c divided by c prime, and the corresponding magnitude of the energy fluctuation, standard deviation of E, which is equal to gamma 0 to the power minus 1/2, would be equal to kt square c prime divided by c plus c prime to the power minus to the power 1/2, because I have already inverted the gamma 0 value. So this would be equal to, if I multiply top and bottom with k, I would have kt coming out of this equation. So kt c prime divided by k c plus c prime to the power 1/2. So this would be equal to the magnitude of energy fluctuations. Okay, so that's the answer I obtained, which is the suggested expression in part A. And now, what is delta E tilde when C prime is much greater than C? So this is basically going back to the problem 5.22 now. So let me look at what happens to this expression in the limit when C prime is much greater than C. Then my delta E tilde will become kt multiplied with c prime k parentheses c plus c prime, but this c will be negligible compared to c prime, and these c primes will disappear. Therefore, I will be left with this to the power 1/2. I will be left with kt c over k to the power 1/2. So if I take k inside, this would be k square c over k to the power 1/2. The k's would disappear. Then I would find the magnitude of fluctuations to be t square root kc. So this would be my answer for this part. Now, if you compare this to what I obtained in problem 5.22, it's exactly the same thing. So this is consistent with the previous result. Now let's move on to part C. Part C says, suppose that A and A prime are both monatomic ideal gases containing capital N and N prime molecules respectively. Calculate the relative magnitude of fluctuations of system A, delta E tilde over E bar. Now this is an application for a monatomic gas. The mean energy is given by 3 over 2 capital N kT due to the translational kinetic energy of the center of mass. And similarly for E prime bar, I would have 3 over 2 capital N prime kT, and therefore the heat capacity C will be del E bar del T, which is 3 over 2 capital NK, and similarly C prime would be equal to 3 over 2 N prime K, which is del E prime bar del T. So I have to substitute this result for delta E tilde. So for delta E tilde, I have kT times C prime, that would be 9 over 4 capital N prime K square. This should be divided by K C plus C prime. So I would have here K 3 over 2 NK plus 3 over 2 N prime K. So I have to add these up. So this to the power 1/2. So this will be KT. Now I have here 9 capital N prime K square divided by 4 K, and then in 3 over 2 K parentheses I have N plus N prime. So This is going to get rid of this 4, it will make it 2. This is going to get rid of this 9, it will make it 3. And then I have k squares, so this k square will disappear. So I will be left with to the power 1/2 a kt 3 over 2 capital N prime over n plus n prime to the power 1/2. So that would be delta E tilde. Now the relative magnitude of fluctuations, delta E tilde divided by E bar, would be equal to kt 3 over 2 and n prime divided by n plus n prime to the power 1/2. And then here I have 3 over 2 capital NKT, that's the mean energy. So this capital KT and KT will disappear. So I will be left with 2 over 3n, 3 over 2 and n prime over n plus n prime to the power 1/2. So if I take this into the square root, this would become 4 over 9 n square, 3 over 2 and n prime over n plus n prime to the power 1/2. So this will give me a 2 here, this will give me a 3 here, and this n would disappear with this n, and I would find that my answer would be delta E tilde over E bar is 2 over 3 capital N multiplied with n prime over n plus n prime to the power 1 over 2. And in part D, examine this expression in the limiting case when n prime is much greater than n and n prime is much less than n. Does your result agree with what you would expect for delta E tilde in the limit as n prime is 0? So n prime 0, n prime much less than n prime much greater than n. So I'm going to examine these cases. So when delta E tilde divided by E bar in the limit n prime is much greater than n. So let me take a look at this. So here I had 2 over 3n, and then I have n prime divided by n plus n prime to the power 1/2. Now if n prime is much greater than n, this n should be neglected. So I will be left with n prime over n prime, and n prime over n prime would disappear. So this would become 2 over 3 capital N to the power 1/2 in the limit n prime is much greater than n. Now if I look at the limit n prime is much less than n, so delta E tilde divided by E bar is 2 over 3 capital N, n prime, n plus n prime to the power 1/2. Now n prime is much less than n, so it should be neglected. So I will be left with an n here. So this is going to become 2n prime divided by 3 capital N square to the power 1/2, which is 1 over capital N 2n prime over 3 to the power 1/2 in the limit n prime much less than n. So I have the two answers here for these two limits for the relative magnitude of fluctuations. Now the question is, what happens if n prime is 0? So if n prime is 0, we would have delta E tilde over E bar, that is M prime is also much less than N, it is 0, it will become 0. So that means there would be no energy fluctuations. So what does this mean? There is no thermal interaction for system A. There is nothing to interact with for system A. So A becomes thermally isolated. Therefore, so that the mean energy E bar will be fixed and delta E tilde will become 0, no fluctuations in E bar, because the total energy will be fixed. So that will be due to conservation of energy, we expect it to go to 0, and indeed that's what we observe. Okay, so we looked at, this is basically a generalization of the previous problem, problem 5.22, where we had a system in contact with a heat reservoir. What happens if we have two systems, A and A prime, and one of them is not a heat reservoir, and these systems are in equilibrium and they have heat capacities C and C prime? Well, the generalization can be found using the results that we have obtained for magnitude of energy fluctuations. So you can review this video. This was basically done on this part where we looked at the probability distribution for this thermal contact, and we have looked at the behavior of the probability in the vicinity of the most probable energy value, and we found that the standard deviation of energy is gamma 0 to minus 1/2, where gamma was defined as the minus the second derivative of ln omega with respect to energy at the most probable energy, or minus del beta del E. So using these results, we have substituted them into our heat capacity definitions to obtain gamma and gamma prime, and we see from gamma 0 to minus 1/2 expression that delta E tilde is given by kt parenthesis square root cc prime over kc plus c prime, and in the limit c prime is much greater than c, that means one system is much bigger than the other one. This is the system in contact with a heat reservoir, because the heat reservoir will have a very high heat capacity. It will take a lot of heat to increase its temperature. That's what it means. So delta E tilde is T square root Kc. That is in agreement with problem 5.22. So this was our result. And now the application for a monatomic gas, ideal gas. Two systems A and A prime consist of monatomic ideal gases with different particle numbers, capital N and capital M prime. We have obtained the most general relative magnitude of fluctuations, and then we looked at the limit m prime much greater than n and m prime much less than n, and we find that when m prime is 0, the relative magnitude of fluctuations should become 0, because that means there is nothing to interact with and system A is thermally isolated with its total energy being fixed.